Alright, welcome to our 18th video of AP Chem. Well, Unit 7 at least. This one's talking about photoelectron spectroscopy. Now, I currently do not have my stylus. I am going to hope that I can get by without it. But, we'll see. One way to measure ionization energies is by using ultraviolet photoelectron spectroscopy. Typically, that's shortened to PES because it's a really, really long name. But it's a technique based on the photoelectric effect. We're about to remind you of the photoelectric effect, but again, PES stands for photoelectron spectroscopy. In the photoelectric effect, incident light ejects electrons from a material. Now, this requires that that photon of light actually have sufficient energy to eject the electron. This is, again, how solar power, solar cells, solar something. There's a word that I'll probably remember in about 5 slides. But solar something works, where light hits metal and pops off electrons, which we can then use to actually make electricity. So, keep that in mind. Light, as a reminder, consists of photons, each of which has energy according to the following equation, where E represents energy, H is Planck's constant, and V, which is actually supposed to be nu, I think, is the frequency of light. We've talked about this before, back in the original atomic theory. So in PES, monochromatic light, meaning light with one color, is directed onto a sample, causing electrons to be emitted. We're then able to measure the kinetic energy of those emitted electrons. The difference between the energy of the photons and the kinetic energy of the electrons corresponds to the energy needed to remove the electrons, also known as our ionization energy. The whole point of PES is to get an idea of the ionization energy of electrons. Now, it often tends to give you the ionization energy of a group of electrons or an actual specific subshell of electrons, but still used for ionization energy. In addition, the electron structure of atoms with multiple electrons can be inferred from evidence provided by PES. It actually ends up being used for an estimation of the electron configuration of an atom. That's its primary use, and that's the primary use you're going to be having whenever you work with it. For example, both the electrons in helium are pretty much identical. They're about the same distance from their nucleus as hydrogen. Now, they're a little bit different because you've got 2 electrons in the same orbital, but they're basically about the same distance. There's not this drastic change. However, in lithium, which has 1 more electron, there are now 2 shells of electron. And in fact, that third lithium electron is quite a bit farther from the nucleus than in hydrogen. This comes from photoelectron spectroscopy. We're actually able to deduce that just that additional electron is quite a bit different. Now, so in addition, different types of molecular motion lead to absorption or emission of photons. Okay, one last little bit of trivia about photoelectron spectroscopy before I start showing you some examples. Is different types of molecular motion lead to absorption or emission of photons in different spectral regions. Now, hopefully that makes a little bit of sense. But what this mainly comes down to is photoelectron spectroscopy is involved with shooting light at something and seeing what happens. It's kind of a summary. Now, different types of light, different types of radiation, however, do different things. For example, infrared radiation. This is actually typically associated with transitions in molecular vibrations. Now, I'll be honest, I've never heard of this before, but I find this really cool. Meaning, with infrared radiation, if we had an actual PES lab set up, we can actually detect the presence of different types of bonds. Now, again, I'm not too sure how that works. Try to keep in mind that infrared goes with bonds, but I mean, that's kind of cool. I'm guessing we can figure out like covalent, polar covalent, probably dealing with how the actual, oh, that makes sense, how the electrons are moving. So, if we find that they're kind of moving in between two atoms, it's probably covalent. If we find they're really only on one side, maybe that's either polar or ionic. It's just, you can actually use light to figure out bonds, which I guess has been around for a couple years. I probably should have known that, but oh well. Lastly, though, ultraviolet radiation, that's actually associated with transitions in electronic energy levels, which is closer to what we're doing with PES, because you can then actually look into the electron structure. You can look into the electron configuration with UV light. So anyways, just wanted to tell you, photoelectron is most commonly associated with ionization energy. That branch of science can be expanded. Feel free to look into that. It'd be kind of a cool field. You're just shooting light at stuff. But with that summarizes photoelectron spectroscopy. I'm now going to show you on the board how this is typically used and what it's looked like. It's just much easier to do on the board, especially when I don't have my stylus. Thanks for watching.